So last time I talked about normality. We're talking about a real number and aspects of how we can refer to it, maybe by b-adic expansion or in other ways, other aspects of the representation of that number. Okay, so and representing it in some way using rational numbers. So if you represent it in base 10, you're approximating the real number by fractions where the denominators are powers of 10, or in binary by dyadic rationals. So normality is a kind of is similar in a way to what we're talking about with modern randomness. That randomness is sort of reflected in the random choices of the individual digits. You flip a coin, flip a coin, flip a coin, and the sequence you get is random. And normality is explicitly the statement that the simple normality is that the digits occur with their expected value asymptotically. This irrationality of exponent is what I think of as a metric in Diophantina approximation, a metric analog of Kolmogorov complexity. Okay, so this definition originated with Leibniz's proof that there are non-algebraic numbers. Real number C has exponent of irrationality alpha. If alpha is the least upper bound, or the least upper bound on a set of real numbers, such that this inequality occurs infinitely often. Okay, so in other words, for infinitely many p over q, right, the distance between C and P over Q is less than 1 over Q to the alpha. So if alpha is large, that means that in the scale of q's, right, P over Q is close to C. And if you think of it in terms of Kolmogorov complexity, the specification, do it in binary, the specification of Q, right, is length something like log Q. Right? And so in P is work between 0 and 1, because the first integer part doesn't matter much. So, and then the information in P is on the order of n and q, because P is some number between 0 and q minus 1. So the P over q is represented in terms of information by something like 2 log q. Right? And what's the information, what that you get out of this inequality for C? Well, you get alpha log q, because you're getting alpha many digits in the base q representation. Okay, so what kind of compression are you getting? You're getting something like, you're specifying lots of bits about C. You use 2 log q information and you get alpha log q out. So you're compressing like 2 over alpha. And roughly speaking, that's optimal. That's the way that it works. Okay, so this kind of approximation of having high exponent irrationality says that the initial segments of C are not too complicated. Okay, so it's like Kolmogorov complexity. All right, good. And in the computational setting, looking at Martin-Loeb randomness as a measure of randomness and incompressibility as a measure of randomness, they identified the same sequences as random. Now, we already saw that normality in one base doesn't imply normality in the other base. And you can have a number that's normal in base 2, but not normal in base 17. And you can pick at random where you want normality to occur, and even subject to small constraints where you want simple normality to occur. Okay, so normality between one base and another is, there aren't causal relationships. Okay. But what about this kind of compressibility versus normality? Right? These are Diophantian approximation versions of Martin-Loeb randomness and you could say Kolmogorov complexity randomness. Can we see the difference between those two things, which is obscured computationally? And the answer is, well, there we go. Liouville numbers have infinite exponent irrationality. That's how Theodore originally used them. If you look at a random real, the exponent irrationality is equal to 2. Which figures if by the calculation that I just sketched out. Roth's well-known theorem proved that irrational algebraic numbers have irrationality exponent equal to 2. That's they look like random reals, which I believe was prompted Borel's conjecture that irrational algebraic numbers should be absolutely normal. Okay, so now, however, there's an interesting non-correlation between rational approximation by virtue of a close rational approximation in terms of exponent of irrationality and normality. And so the typical way that people prove normality is it's a characteristic of randomness. Right? If you use Lebesgue measure, like almost every, with the set of reals that are not normal, absolutely normal, is a null set. But that's not the only kind of measure that's for which a random real is normal. There are estimates that it's typically these are done analytically, and there's estimates you can get on for which measures does a random real have the property of normality. And that has to do with the Fourier transform of the measure. And so the first thing that happened is Bloom, based on prior results of Kaufman, there's a measure nu which is supported by the Liouville numbers. So the Liouville numbers are random with respect to this measure, and the Fourier transform vanishes at infinity fairly fast, which is an indicator of uniform distribution. And Peugeot converted that into proving that there's an absolutely normal Liouville number. So it's very well approximated by rationals, right? But in every base, it's normal. And then Peugeot posed the question, and Batcher, Heiber, and I showed that there's a computable such example. And it comes from decomposing. You also, similarly in doing a construction, you have to start specifying the digits and do some kind of now let's say what the next digit is, what the next one. You always have to look ahead that you never leave the path along which you can ensure that the digits are becoming equally distributed. And that involves estimates that come out of looking at these measures. Okay, it's open. It's open. There isn't a polynomial time computable even close to linear time by a result of Lutz and Mayordomo. There is a polynomial time computable absolutely normal number. It's open whether you can give a fast algorithm to produce a number like this. Okay, so that tells us that Diophantine characteristics of randomness can be separated. You can look highly non-random in that you're a Liouville number from the point of view of approximation of the initial segments. At the same time, looking statistically random because the digits in every base are equally distributed. So you get to see aspects of randomness in this context that you can't see computationally. That leads to an interesting problem which I'd like to pose. I mentioned this one to Bjorn in Cambridge, but let's get it out for anybody to give it a try. You could look at restrict your Liouville number. Being a Liouville number means you have these nice rational approximations. For implementing P over Q, right? The distance between C and P over Q is less than 1 over Q to the K. And that's true for every K. So now you could restrict yourself, instead of looking at arbitrary rationals, let's look at rationals where they are p-adic rationals. The base is a fixed number. So Liouville in base B, and means you only get to use p-adic rationals. Okay, so here's a question for which I don't know the answer. Is there a C which is normal in base 2 and Liouville in base 3? So can you have a number that is very well approximated by triadic rationals, but vis-a-vis normality looks random for dyadic rationals. So I don't know the answer to that. That there is a strange example due to Stoneham, which can be converted to say that the answer is yes if you look at the numbers 2 and 6. But you have to use, this is a product of two primes, and there's a sort of number theoretic quirky thing that you can exploit. Okay, so that's it for normality and Liouville numbers. But these Liouville numbers will return in a well, not Liouville hasn't finished yet. Liouville is coming back. What did I just do here? Okay, so on to the next walk. But I promise you that you're going to see Liouville numbers again. So today, in my last talk, I was building up to this all week. This is the Hausdorff Institute. And so I wanted to end on a Hausdorff note. So I'm going to talk about computability and Hausdorff dimension. And in a particular generalization of Hausdorff dimension that's called gauge dimension. Okay, so the question that we will kind of circle back on various things that we talked about this week. So the question that is addressed by notions of dimension, right, is this one. Well, it's not this question, but dimension is meant to address the notion of size. Right? How big is a set? What's its extent? How thick is it, or how well distributed is it? And the question that I want to discuss today is a question which you could view as a question of definability. You have some set, and you want to know, like, how is its size reflected by the easily defined sets which it contains. Okay, so that's some arbitrary set, who knows where it came from, or whether it's definable in any way at all, right? But to what extent is the structure of the set, right, supported by or indicated by the structure of its definable subsets? And the more simple the definition for the subset, right, the stronger the conclusion that we understand what is the driver of size, because we understand what a closed set is, or we think we do. Okay, so to what extent can the size or dimension of the subset of Rn be duplicated by one of its closed subsets? So we've already seen a couple of examples. And if you're looking at Lebesgue measure, then for an arbitrary set, if it's measurable and it has, I guess I don't even need to know that it has positive measure. You can find a closed subset of it which supports its measure or its size in the sense of Lebesgue, right? Up to arbitrary epsilon. So, and then if you're allowed to take a union of closed sets, if you take an F sigma set, right, you've captured that's a very simple set. It's a sigma 0,2 set. And so if you take an F sigma set, you've captured the entirety of the weight of A. A looks like a sigma 2 set with some spray paint on it, right? And what's the spray paint? It's a null set. It's just some kind of hazy fog. If you wipe the condensation off the mirror and see clearly. So for Lebesgue measure. Now this fact, we realize very strongly on the fact that Lebesgue measure is a sigma finite measure. Rn is a countable union, that's a finite Lebesgue measure. Okay, and secondly, we also mentioned this, that if you have an analytic set and it's uncountable, then it has a closed, uncountable, perfect subset. Okay, so the cardinality of an analytic set, this is not an arbitrary set, it's an analytic set, and we already saw it's consistent with the axioms of set theory that there's a co-analytic set for which this doesn't apply. Okay, but for a fairly fairly large definable class, the uncountability of an element of that class, right, is determined by a very simple subsets of that element. Okay, so, all right, so.
So are you saying that every Lebesgue measurable set can be written as a union of an F sigma set and a null set?
Yeah.
Oh, I thought there are sets sort of arbitrary high complexity in the Lebesgue measure sigma algebra.
Yeah, but they're null. I mean, it's the measure of the set. The measure of the set is supported by a concrete object. And then the membership, right, the actual numbers in the set, that's what I'm calling the spray paint. And you get lots and lots of new sets, but the weight of them, right, has already appeared very early. Okay, so now, how is Hausdorff dimension, wherever he is here, how is Hausdorff dimension defined? So Hausdorff dimension is defined by, so size, right, is typically size, length, area, volume, those aspects of size. Right? So that question, right, was studied for a long time, and that was the genesis of the ideas of measure. What's the size of in the sense of Lebesgue, what's the size of a set? Well, it's Lebesgue measure. What's the size of a set that's, now there are lots of null sets, like we just mentioned. Okay, so some sets are more null than others. Right, so how do you sort of account for sets that have positive measure and all the others? Well, so Hausdorff addressed that, right, to give a family of measures so that they were more finely granulated than just Lebesgue measure positive or Lebesgue measure null. So it's a way to account for variations of size for sets that are null. If you're thinking of it in the line, subsets of the line that are null for Lebesgue measure. You could try to think of, let's look at two sets. One is the Cantor middle third set, where you start with the integral and throw away the middle third and iterate that process. And how about the Cantor middle 1/billionth set? You throw away a billionth and then a billionth. Those two sets are both null. But one of them is thicker than the other. Right? So it's they're both like a lacy subset of the line, but one of them is harder to see through. Okay, so anyway, so Hausdorff dimension. So you define a family of measures. And this is how they're defined. So HS of A, that's the Hausdorff S-dimensional outer measure of A, is the limit as R goes to 0. So think of R as a kind of granularity. We're going to use smaller and smaller basic open sets. So as the granularity goes to 0, and now you do the usual thing for measure. You take an open cover of sufficient granularity, all the diameters are less than R. Right? And then you look at the diameters of the balls that are used in that cover, and now we're going to weight. How much weight are we going to give to, or what's the size that we're going to attribute to a ball? Well, it's the diameter to the S. So in Lebesgue measure, if it were the line, you'd just say, well, it's the sum of the diameters it's the sum of the lengths of the intervals, right, that appear in the cover. But now we don't want to count an interval by its length, but we'll count it by something bigger than its length. Right? And that way, it's easier for a set to have positive measure. Right? So if we're putting a much higher cost in using a ball than just its diameter, like these are less than 1, say, so the square root of the diameter is going to be bigger than the diameter. Okay, and so that gives you so that's how it works. Okay, so as the weight we put on a ball in part of an open cover, as that weight is bigger and bigger, it's easier for sets to have positive measure under this definition. Okay, so that's the Hausdorff measure, if you fix R, that's called we'll come back to this H sub S, HS sub R. Right? And HS sub R is just without the limit, it's a nice continuous measure, and just like Lebesgue. Okay, one thing to note about these measures, if we're looking at S less than 1, then the real line is not sigma finite. Or if we're looking at S less than 2, like if S is equal to 1, and we're looking in the plane, we're sort of looking at linear measure, right, for subsets of the plane. Well, the plane is not going to be a countable union of things that finite linear measure. The plane is not a countable union of line segments. Okay, so here's the picture. This is the square root function, that's the linear function. As we weight these sums, we're giving this weight if we're looking at h1 half, and we're giving that weight if we're looking at h1. It's easier to have positive measure if the function goes to 0 more slowly. Okay, Hausdorff dimension is defined, it's the sup of the s greater than 0 such that h s of a is equal to infinity, right? So, or 0. And that's by a fairly elementary calculation, the inf of the s greater than 0 such that h s of a is equal to 0. So there is a sweet spot where as you vary the exponent, there's a sweet spot where the set goes from looking like it's null to the set looks like it's not even sigma finite. That sweet spot is the Hausdorff dimension. Okay, so it's the Hausdorff dimension it's a number because these measures are parameterized by numbers. But we're using the power functions that what's the weight of a ball? It's the diameter to the s. So we're using the power functions to give us a one-parameter family of measures. And for that family of functions, the power function, there is this transition phenomenon. So it's a property of the power, of a particular family of power functions, which ones give the set infinite measure, which ones give it 0 measure. And then a number pops out because those functions are parameterized by numbers. Okay, now, a line segment in Rn. This is one advantage of this is that it doesn't matter. It's agnostic as to what the ambient space is. It doesn't matter. A line segment viewed as a subset of a line, or a subset of the plane, or the subset of including free space. It doesn't matter where you look at that line segment, you get the same answer. So a line sitting inside the plane, viewed in the Lebesgue measure in the plane, is null. But this gives you a kind of dimension-free analysis of the intrinsic property of a line. The Sierpinski triangle has Hausdorff dimension log 3 over log 2. So it's not, there's more to the Sierpinski triangle than a line segment. There's a lot less than the whole plane. And you would distinguish between the middle third Cantor set and the middle billionth Cantor set. They have different dimensions in this sense. Okay, and then this is a good one. The path of a Brownian motion in Rn, n greater than or equal to 2, has Hausdorff dimension 2. So you take a Brownian motion in R3, and this little jittery bug flying around. It has dimension 2. All right. Gauge functions are a generalization of the power functions. And so the power functions are quite nice functions, but there are other functions in the mathematical zoo than just power functions. And a gauge function is any function with the properties that are shared by the power functions. It's a continuous function. It's increasing, right? And the limit as x goes to 0 from the positive side of x is equal to 0. Okay, that's a gauge function. All the power functions are gauge functions. And for any function like this, we can associate a Hausdorff outer measure in the same way that we did for the power functions. We didn't use anything special about them. And we have the same sort of picture. We say that that G is higher order than F. We indicate that G goes to 0 faster than F does. Okay? And the faster that the function goes to 0, the harder it is for a set to have positive measure for the associated gauge measure. And so if F goes to 0 more slowly than G, then we're saying that the set has G measure bigger than 0 means that it's bigger. It has higher dimension. So it's a little, if this is unfamiliar, then it's a little tricky because the function that goes to 0 faster is bigger. But it indicates a bigger size. That's, all right, so now, and this same sort of sweet spot, the transition that I was talking about, works for arbitrary gauge functions. Namely, if H is of lower order than F, and the H outer measure of A is less than infinity, then A looks null for F. And so if you are not infinite for something of lower order, you are null. You are null for anything of higher order. And so that's what's, you look big until you look small. And then this is just the converse. If G is higher order, so both of these things, like I'm saying both, even though they are the same statement, really, keep them in mind. Right? So the higher order and A looks positive, and it looks not even sigma finite for any lower order. Okay, so a set determines, yeah, go ahead.
Is this ordering not linear?
It's non-linear. Because you can have these functions that cross each other going down. They can't go up. You can have them go down, and then this one goes down fast, and the other goes slow, and then they just cross it. So it's, in fact, so here's the set of gauge functions which give a set positive measure. Right? They sort of form an ideal. There's no join here. They form the lower part of the partial order of gauge functions. And the ones that say that A has measure 0, they form something like a filter, an upper set in the partial order of gauge functions. And that partition, we call the gauge profile of a set. It's just a complete account of which gauge functions does the set have positive measure. So for which gauge functions does the set look big? That's a very finely granulated or calibrated account of the dimension of the set. Okay, so here's a highly conceptual. There's no axes here. This is just the white part is the gauge functions of higher order, and the red part is the gauge functions of lower order. Red means that the set looks a positive measure, and white means that it looks like it's null. Okay, so, and that blue line is sort of the parameterized line of the power functions. So this is some sort of conceptual rendering of the gauge profile of a set that has some kind of Hausdorff, it's not null for the Hausdorff measures. There it is. Okay, so if you're trying to understand what are the possibilities here, there's lots of natural questions you could ask. You could ask, let me write down a couple questions here. All natural questions. Well, suppose we have particular sets. What is their profile? So you could look at interesting sets that come up for other reasons, and try to figure out what's the size of that set in this finely calibrated sense. Or there's an interesting part here, right? The boundary. Well, what can happen in the transition? What are the possibilities? How about simple sets? What are the possible profiles of simple sets, or Borel sets, or even of arbitrary sets? And then the question that I posed at the beginning is how much of the profile of a set is duplicated by its closed subset? So again, is the gauge profile of a set captured supported by a closed subset. So that's called computability. Okay, so here's an example. So this example of Brownian motion. If you almost surely the path of Brownian motion in Rn has finite positive HF measure for f of x equal x squared log 1 over x. Okay, so it has Hausdorff dimension 2, but there's more information there. If you expand the way you can resolve differences in size to include these gauge functions, you get a very fine analysis. Right? So you get a point on the boundary of this picture for a Brownian motion. Right? Because this has finite positive measure. That means it's infinite for everybody that is lower order than this, and it's null for everybody that's higher order than that. Okay. So you get it. These gauge functions are useful for understanding natural examples. I mean, I can't claim that they're more. I mean, Hausdorff dimension is extremely useful. It appears all over the place. Gauge dimension is a more of a niche topic, but still, it has its advantages. Okay. So some comments about what can happen on the boundary. So this theorem. There was a big surge of investigation on these kinds of questions in the 1950s and early 60s, or even into the 60s, early 70s, and a lot of activity sort of was in orbit around Besikovich. So we'll see Besikovich a couple of times. Okay, so Besikovich proved that if h of f is null, right, so if A is null for the gauge measure HF, then there's something of lower order, right, such that A is null. This is arbitrary A, such that A is null for that gauge measure also. So you can't have a gauge function, right, that sits on the boundary between null and infinite, right, for which the set under discussion is null. That's unlike Hausdorff dimension. In Hausdorff dimension, where you just use the power functions, every possibility can happen at that transition point. Which was, I suppose, why Besikovich wanted to check it for the gauge, in the gauge case.
Can you go back to the previous slide?
What, sorry?
Can you go back to the previous slide?
Sure.
I'm getting confused about the direction of the order.
Yes,
So
sir.
x. So
There's
x
the order.
cubed, which x cubed is whatever.
The faster that you go to 0, the higher order.
So x squared is less than x cubed.
X squared is less than x cubed.
So then why on the next slide, why on that other slide was x squared log? Seems like that's the bigger function. Oh. Log.
It goes to 0 more slowly.
Oh, it's big. Oh, sorry, I'm getting.
Yeah, that's what I said. It's confusing. It's the thing. That's why I drew these two pictures, right? So the thing that goes to 0 more slowly makes it easier to have positive measure. No, this happens it takes 6 months before you stop doing it. No, but thanks for this.
I got 5.9 months.
Right. Okay, so. All right, so if the measure is 0 for A, then F doesn't pick out, right, a point on the boundary of the gauge profile for A. In fact, F is in the white region. It's separated from the red region. Okay. Based on Besikovich's argument is a fairly elementary argument. It's short. Now, and based on that argument, Rogers, if you are all interested, Rogers wrote a very nice book called Hausdorff Measures, and this material is covered there. But so he raised this question, which let me go back to this picture. The question that he raised is, could the white region have an omega cofinality going down? Could it be that there's a countable sequence in the white region such that everything that's below the sequence, right, is red? So could the cofinality of the white from the top be omega? That's the question. Okay, so suppose that you have a sequence of gauge functions so that it's decreasing, f of I is of higher order than f of I plus 1, it's going down. And A looks null for all the fi's. Okay, so that's the setup. You have a cofinal omega sequence going down in the white region. Does there exist a gauge function H such that H is of lower order than all the fi's, and H also gives a measure 0? So could it be that, is it the case that the white region doesn't have cofinality omega decreasing? And he expected the answer to be yes. Basically, and it even says so, that Besekovich's proof could be adapted to this context. I mean, after all, these measures are countably additive and countable. You always mush together countably many things, and countable union in null sets is null, and so on. Okay, but they're not null, in this case, not null for the same measures. We have a sequence of measures. Okay, so he expected a positive answer, and Rogers and Taylor proved that the answer is yes, if A is sigma compact, a countable union of compact sets. So for very concrete sets, the answer is yes. Okay, so now, the answer is no. And you can once you start thinking about the problem, you can extract a counterexample by looking at the set of Liouville numbers. The Liouville numbers are a natural class that refute the intuition from the Rogers question, and there was prior work of Olson and Renfro, from which you can extract what you need to prove to check that they're a counterexample. But the general theorem is this. So suppose you have a sequence of gauge functions, and it's decreasing in order. And then there's a pi03 set, such that the following conditions hold. It's null for all the h of fi's, and for all gauge functions that are of lower order than all the fi's, A is not sigma finite. So it's not a property of the power function. It's not something that's tied to rational approximation. The Liouville numbers give you a nice paradigm, but it doesn't really matter what functions you're looking at. And you don't have to go to a weird set. It's not like we're talking about V equals L and coanalytic sets of strange sort. Right? It's a pi03 set. Okay, so I'd say a little bit about the proof about this, but before I get to the proof, or the discussion of the proof, I want to mention another example, which I think is quite interesting, and a corollary, and then we'll look into the ingredients of the proof. Okay, so here is the other example. So it's, you know that the concepts of measure and category are distinct. Right? So category, a meager set, is a countable union of nowhere dense sets. Right? So a co-meager set, right, consists of a set of reals such that those reals meet countably many dense open sets. So in computability theory and in set theory, right, you have a co-meager set, you say that its elements are generic. They meet countably many dense open sets. That's a generic real. So that's a real in the sense of a category. That looks what we say random looks like in the sense of matter. And there is a co-meter set of zero Lebesgue measure, and there is the set of one randoms, which is co-null, is meter. Because they're all normal. And so they don't have that they don't meet the dense set, that there are implementing L such that following the first L bits, you see all zeros for another L bits. Okay, so category and measure are usually viewed as orthogonal notions of large. But if you use these gauge measures, you can exactly quantify to what extent are category and measure orthogonal. And so here's the theorem. This is made by Peng Mao, who's a graduate student. So look at the set. So this scales, but I took a particular example. Look at the set of arithmetically generic reals. Those are the reals that meet every arithmetically definable dense open set. Okay, so that's a definability theoretically. That's a very natural class of, a calibration of how much genericity. Okay, and then, so that's a nice co-meter set. And then for a gauge function, it gives that set a positive measure if and only if, for all arithmetic gauge functions G, this derived function from F is not of higher order than G. Okay. And what is this F? It's just a smoothed out version of F, which generates the same measure that F does. Okay, so you can give an exact account of which measures make this co-meter set have size. And so it's Lebesgue measure doesn't attribute size to a co-meter set, but the measures that do can be completely characterized. So it's an interesting, so this kind of point of view can shed light. I said, you might want to figure out what are the gauge profiles of sets of interest. Well, the set of generic points, right, for the topologically random points. I mean, that's a set of interest for us. And you can give a complete account of how gauge measures and genericity are related to each other. So that's a nice example, I think, of what this apparatus can inform you. And it uses some ideas from this Diophantian approximation. Olsen and Renfro were the ones with the Liouville numbers. Okay, so now, so we're discussing now this capacitability question. So I'm going to come back to this, some comments, and I'm going to come back at the end to this pi03 thing. So capacitability, if you have a set of positive, a measurable set of positive Lebesgue measure, it has a closed subset of positive measure. Okay, so Davies proved that, this is in the 50s, if A is analytic and it has positive gauge measure, then it has a compact subset of positive gauge measure. This is for a single gauge measure F, so it looks like Lebesgue measure, except you have to work with analytic sets rather than arbitrary sets, and that's a reflection of the fact that these measures are not sigma finite. You can't like fill it up except for its complement. It's both the same. Okay, and the same thing is true for when A is not sigma finite. If A is analytic and not sigma finite for HF, then it has a compact subset for which it's not sigma finite for HF. Okay, so the size, the HF notion of size, right, of a set is supported for analytic sets, supported by what happens with the closed subsets. So that's sort of the simple sets carry weight. Okay, now, we had this set that we discussed about co-analytic set with no closed uncountable, an uncountable co-analytic set with no closed uncountable subset. That example, which was this X can compute the ordinal which it's constructed, that set. If you look inside L, you can compute the Hausdorff dimension of this set. It has full dimension. This is a dimension 1 set. If V equals L, it's a dimension 1 set. It's reasonably simple in terms of the form of its definition. It's a pylon 1 set. And full dimension and all its closed subsets are countable. So it's a meta-mathematical situation. Right? How well do closed subsets support dimension? Well, maybe for co-analytic sets, maybe not at all. So the question of computability has interesting logical aspects. And if you assume stronger set theoretic hypotheses, then you get more of the axiom of determinacy, and you get that this disappears. You get computability for larger and larger fragments of the definable hierarchy. Okay, so there are interesting meta-mathematical things that come up with regard to these notions of dimension. And then here's the corollary. So I mentioned, and we'll say a bit more about it. There are pi03 boldface. That's meant to be a boldface thing. So you need a real parameter. Okay, so there are pi03 sets A, such that for any closed set C contained in A, there's a gauge function such that it says A has positive measure, in fact, infinite measure, but C is null. Okay, so if I fix the gauge measure, and A has it's pi03, it's analytic. Right? So if A is positive measure for a particular gauge measure, then it has a closed subset that has positive measure for that gauge measure. But if you look at the sort of full gauge profile of the set, for any closed subset of A, there is a measure, right, such that A looks big with that measure and C looks null for that measure. Okay, so how do you get this kind of example? So I said it's a corollary. So how do you see this? Well, let A be any of the counterexamples to the Rogers question. So there is this countable sequence decreasing in order, and A is positive for every measure that's parameterized by a function that's below everybody in the sequence. Well, a closed set cannot have that property. If a closed set is null for everybody in the sequence, it's null for somebody below all the things in the sequence. That's the Rogers-Taylor theorem. And so take a set that has this countable cofinality from above, and any of its closed subsets, that null property spills down. But it doesn't spill down for A. Okay, so A is for any particular measure, you can find a closed set that's positive, but there's no one closed set that fills A up for its entire profile. So there's a structural difference, right? In this account of dimension. There's a structural difference that appears at pi03 versus pi01 or even sigma 02. So there's a new dimension that appears at level 3 of the Borel hierarchy. Okay. All right, so now let me return to the proof. And we have 11 minutes, so that's pretty good. Okay, so theorem, just to say the theorem again, you have a decreasing sequence of gauge functions, Fi, and this is the theorem to prove, we want to exhibit a pi03 set such that it's null for all the gauge functions in the sequence, and for anything that's below all those gauge functions, its measure is infinite. Because that's what to do, what we should do. Okay, and here's the outlines. I'm taking a page out of Bjorn's lectures. It is a 4-step process. And the process is, in outline, we're going to transition away from the general definition of gauge measure, the original Hausdorff definition, to what are called net measures. Okay. And, well, I'll say what they are in a second. We're going to invoke a theorem of Vesickovic that if you have a set that has, if you have a closed set and it has infinite measure, then it has closed subsets of every finite positive measure. Okay, so if you have a set that's big, closed, you can find a subset which is not so big, but still positive. That's not obvious, because these measures are not sigma finite. Right? So it's awkward to work with a measure that's not sigma finite. Then we're going to invoke Besekovich's theorem. Right? The sets that appear as the result of Besekovich's theorem, we're going to view them as conditions in a forcing construction. So, and then we're going to look at the set of sufficiently generic reals for that partial order, and that's the pi0 3 set. So it is a direct application it's a conceptually direct application of sort of techniques that show up in computability theory, namely forcing and arithmetic, and looking at things of limited genericity and controlling how they work. Okay, so it's the notion of genericity, but which is a bare category notion. All right, so net measures. So this, as far as I know, that this was first applied in this area by Besekovich. If you look at, when we defined the way that Hausdorff dimension worked, we looked at arbitrary open covers as a union of balls, and then we took the weighted sums of the sizes of these balls. Okay, so now, there are a lot of basic open sets, because there are a lot of diameters. It's hard to do some kind of discrete analysis. It's hard to do a kind of inclusion theoretic analysis when you have to, when the basic objects you work with are described by arbitrary reals. So Besekovich showed that if you first, it doesn't matter if you use closed sets in your cover or semi-open or open sets, it doesn't change whether sets have infinite or finite positive or zero measure. And it also doesn't matter if you restrict yourself to open covers which are unions of dyadic basic open sets. So a dyadic basic open set would be something in the line like from n over 2 to the k to n plus an interval from n over 2 to the k to n plus 1 over 2 to the k. If you only look at intervals like that, atomic and dyadic intervals, you get the same distinction between null, finite, positive, and infinite. Okay, so in terms of computing dimension, not numerical size, but just dimension. Dimension is determined just by this distinction. It's like a line segment of length 1 and a line segment of length 2 have the same dimension. They have different length, but the same dimension. So that doesn't really make much difference. Okay, so that means you can go away from continual many basic open sets to just countably many. And the way that the proofs go look a lot more like working on 2 to the n. And finite initial segments are little dyadic intervals. So you're in the realm where we have experience in computability theory. That's the kind of stuff that we work with all the time. We call those, 2 to the n, we call reals. So you can do that. You can move to a context where computability theoretic methods are applicable. Okay, then the second thing is this theorem of Besekovich, which is a closed subset C of infinite HF measure has closed subsets C of any finite measure. Okay, so I use C in 2 different ways, but we do that all the time. Okay, so you can restrict yourself. Now, what's good about a set of finite measure for say HF? We have this decreasing sequence F1, F2, F3, F4. What's good about a set that has finite measure for H4? Oh, it's null for all the previous ones. So if I have a real that is a member of a set that's null for each HFI, so being a member of a set that has finite measure, so suppose I have a set X, and suppose that for each I, X belongs to a set that has finite measure for HFI, then it's null for all the F's. Because if you were in a set of finite measure for HF 100, you're in a null set for HF 99. So finite measure is useful for us So let me, in the interest of time, I'll say very little about the proof, or the truth. So just remember that you can thin a closed set of infinite measure down to something of finite measure. Okay, so that's step 2. Step 3, put together a forcing partial order. Now let me, I wrote something down here which I'm going to draw a little picture of. Closed set is a collection of paths through a tree. So if we have a set that is, so F0, C0 is a closed subset of 0, 1, such that HF0 says that C0 is measure 1. So it's a set of paths through a tree. And we're trying to think of a forcing order, or like a step-by-step construction. Okay, so inside this, there's some neighborhood. Right? Here's an initial segment of a path through the tree, and here's the neighborhood that goes after that. This is a nice, the pass through here is a nice closed set. Okay. We could thin that down. And now this thing that has HF of C0 greater than 0, this thinned down part could have H, this is F0, of HF1 of, I don't know, call this sigma, call that C sigma, this thinned down version. Is less than infinity, but greater than 0. Okay, so that will be a step in the construction. That's how you refine the condition C0 to get a new condition, which is a finite measure for F1. It is null for F0. Right, and then inside there we could thin out, we could repeatedly thin out at each node to get a set that has finite measure for HF2 and HF3, and that's what this all says. So you can think of these thinned out Bezikovich sets as conditions in the forcing construction, or as steps in building something. Okay. Okay, so then what's the pi03 set? It's the set of reals that are generic. So for every I, right, the real is a path through one of these thinned out neighborhoods in the iterative application of Bezicovich's theorem. Okay, so it says for all n, there exists one of these thinned out sets, Cni, in the collection of sets that we constructed by applying Bezicovich's theorem, and X is an element of that closed set. X is an element of a closed set is a pi01 property. So let's say for all there exists some element. So for all X, there exists an N and an I such that a pi01 property is. That's a pi03 set. So that's a simple Borel sign. And this set has the property that was mentioned in Roger's question. Namely, it is a set of generic. Generic can stay inside this really big set for a long time. It can look random with respect to F0 until this function that goes to 0 more slowly than F0 is bigger than F1. Then you can dive into something that has positive measure for F1. Look random for F1. But you're looking random for F1 means you're looking random for the thing that has lower order than F1. So you just look random until the thing of lower order is dominating F1. Then you look random for F1 until the thing of lower order is dominating F2. And then you look random for F2. So that's an intuitive explanation. If you want to be more formal about the proof, well, I can reduce that right to a problem that we've already solved, which is there's the proof. Okay. Now, what is interesting here? Okay, so here, do you recall, right? The Borel hierarchy is a proper hierarchy. For every countable ordinal, you get a universal set, which allows you to do a diagonal argument. Which allows you to prove that for every countable alpha, right, at alpha plus 1, there is a set in the Borel hierarchy which was not obtained at any step up to alpha. Okay, that's the diagonal argument. Do you know who first proved the Borel hierarchy is proper? Hausdorff. Hausdorff proved the Borel hierarchy is proper in 1914. Okay, so here's a conjecture. Right? There's a difference. So here's a conjecture that says there's another way, a non-diagonal. There's another reason, not a diagonal argument that could explain the properness of, or establish the properness of the Borel hierarchy. Namely, for every countable alpha conjecture, there is some countable beta bigger than alpha, and a set that is at the beta'th level of the Borel hierarchy, and its gauge diminishing profile is new. It's not represented by any sigma alpha set. So the Borel hierarchy, the conjecture is that the Borel hierarchy doesn't only exhibit new sets, which have this kind of null property that they're just little bits of paint or some kind of sparkles around the real sets that we constructed early. Right? But that there are new shapes that occur cofinally in the Borel hierarchy. And the way that you can visualize them is use this generalization of Hausdorff dimension. So that's the conjecture. And we know that the answer is the conjecture is true. 1 and 2. Otherwise, it's open. So it's an intriguing possibility to shed light on that. This part of the hierarchy of definability from the point of view of geometric measure theory. There's a disadvantage to the way that we have started. Is that the way we've started is structural. Right? In other words, the cofinality omega difference between pi03, between some pi03 sets and the pi01 sets. It's unclear how to take that kind of structural distinction. And you can only use countable cofinality once. Right? You can't use it again because there are pi03 sets that have the property. You can't say, well, now take a pi05 set that doesn't have it. So what is the structural aspect, what's the geometric aspect of things that would allow you to run this kind of distinction through the transfinite open. Okay, and with that, that's the end of my class.
Do you have any more questions for Ted for this and other lectures?